You can't really damage a liquid structurally. Seriously, go try hit a lake with a hammer and see what happens.
Today we're going to be looking at PBS space-time. Specifically this wall, the final barrier to nearly infinite energy. Nearly infinite. Mathematicians aren't going to like this. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge.
They say fusion is 50 years away, and they've been saying that for 50 years.
Wow, that's even more pessimistic than what I've been hearing. I've been hearing that 20 years away 40 years ago, and it's always 20 years away. I mean, I guess the number really doesn't matter if it's always 20 or always 50, but all right.
But if so, why are billions suddenly being pumped into fusion startups? Well,
I don't know. People have spent billions of dollars on SETI, Search for Extraterrestrial Intelligence, and we haven't found any confirmed results, at least not ones they're telling us about.
LLMs. But there's a reason that the techno-brats are bullish on fusion in particular. The fact is, the technological challenges have been chipped away at and in many cases solved over the past decades. And there's really no one deal-breaker difficulty remaining.
Gonna need to elaborate on that. There's still quite a few challenges. Plasma stability being the biggest operational one.
One of the final challenges is deciding on the physical vessel to contain our mini artificial stars.
That's a great one, yeah. Containment, that's a very important one too.
We have some pretty sci-fi options that are nearly ready to go.
This is my first time watching this channel, by the way, so I don't entirely know what to expect.
Solar power is the ultimate in clean energy, and it's delicious when you can get...
I think I know what he's getting at for the narrative of this show, but no. Fission reactors are the ultimate in clean energy based on what we have right now. Fusion would be cleaner, and plus you can also make the argument that solar is indirect fusion. Somebody built a fusion reactor for us billions of years ago, and we're just, trying to get a teeny tiny piece of it. And I mean teeny tiny piece.
Which isn't everywhere all the time. But solar power is just fusion power that's happening far away. Slam hydrogen nuclei together into helium, and a bit of the original mass is
Was that a ring that he put around Earth, or is that just a cursor?
Converted into energy. In the core of the sun, that energy mostly radiates into empty space, with a minuscule fraction hitting the Earth and powering nearly all of life. A minuscular fraction hits our solar panels, and only in, sunny places and times. There's a limit to how far we can scale solar energy collection until we build our Dyson sphere. But why build a cage around the star if...
One thing to point out, and I'm glad he's mentioning that, and solar power involves the use of radiation. After all, sunlight is radiation.
You can instead build a star inside a cage. What?
Artificial stars, all right. I'm assuming he just means fusion reactors, not suggesting we try to build a gravitational confinement reactor, which is how a star works on Earth. Because how those fusion reactors work is... So any fusion reactor works at all is you need extreme temperature, extreme pressure, and confinement time. Temperature and pressure, you're going to get there due to gravitational pressure at the core of the sun at 15 million degrees Celsius, which is actually relatively cold compared to fusion reactors on Earth. But the pressure and gravity is so strong that you can get away with that. On all these closely packed hydrogen nuclei, you can even get hydrogen-1 to fuse, or protium as some people call it, on the sun. Quantum tunneling overcoming the Coulomb barrier. And there's a nice natural balance between the radiation pressure pushing outward and the gravitational pressure pushing inward in the sun. Very sustainable, billions of years. But if you try to make that kind of gravitational pressure on Earth, you're going to have a lot of problems.
Can run mini suns right here on the surface of the Earth.
Okay,
that's
looks
the
like
goal of the artificial fusion reactor. Today, I want to talk about a specific aspect of fusion, and that's how to confine hydrogen fusion in a way that leads to a net energy output.
Okay.
I want to talk about how to bottle a star. I'm going to reference ITER a lot, that's the European fusion experiment.
Alright, so ITER is a tokamak style reactor. Uses magnetic confinement instead of gravitational confinement. Way better off using electromagnetic forces than gravitational forces to do something like this on Earth. Requires very high current, superconducting materials, and the biggest challenge with that is stability of your plasma.
And I'll refer to it because it's the largest and arguably the most advanced, and is projected to achieve first plasma this year.
Yes, I remember that announcement. That was a couple of years ago, though. I don't know when's the last time they reviewed information from ITER, but they're looking more like next decade now, just due to construction delays.
I emphasize, though, that there's a lot of exciting stuff in recent years from smaller efforts, both national programs and, increasingly, private endeavours. We'll come back to some of the more speculative advances another time.
Speculative.
Let's start by taking whatever lessons we can from the Sun. Our home star sustains a steady rate of fusion for billions of years because it confines its nuclear inferno by crushing it under the weight of 100,000 Earths.
High pressure. It's one way to do it. Can't really do that on Earth because we just have one of those, and we don't want to use the whole thing for a power plant. That'd be interesting.
Single protons, hydrogen nuclei, are fused in a series of steps to produce helium-4 plus a lot of energy. The Sun's proton-proton chain runs at something like 100 million Earth atmospheres of pressure.
Yeah, single proton hydrogen, not particularly fuel efficient on Earth, but when you have the Sun, I mean, you have so much hydrogen, it doesn't really matter.
And over 50 million Kelvin temperature, generating the equivalent of 20 million times the entire world's nuclear arsenal in energy every second.
Okay, every second, I was going to say, yeah. Yeah, nuclear weapons got nothing on the Sun. In the grand scheme of things, they're really not that powerful. I've done a whole mess of videos debunking why they can't destroy the Earth or even render it uninhabitable for humans. Please check those out if you haven't already. But yeah, nothing compared to a star.
So, the Sun both crams photons together and gets them moving really fast in order to get them to stick. I
think you meant to say protons. I mean, yeah, you could argue it does use photons. There's a lot of gamma radiation and UV radiation and visible light for that matter, so photons are crammed, but they don't really have much to do with fusion.
Do the same. We need to both compress and heat our nuclei. And the resulting fusion needs to output more energy than when used to reach that state. One big efficiency
Otherwise, it doesn't last for very long, and you essentially don't have a reactor. You have something that just kind of fizzles itself out. That's actually kind of how fusion is weaponized in nuclear weapons. You have fission that creates things that are hot enough to create conditions for fusion, but you just burn all your fusion fuel out. None of it's sustained. Weapons are not designed to be sustainable. They're designed to just go off. That's why nuclear fusion was weaponized for many, many decades before we've even made it this far with fusion reactors.
Is to focus on the most energy-rich fusion reactions. Rather than going all the way to helium from single protons like the Sun does, we can fuse heavy hydrogen isotopes like deuterium and tritium. Now, the Sun can achieve net energy gain starting with protons because of the incredible densities it reaches. We can never achieve those densities, so even with heavy isotope fusion, we have to compensate with a lot higher temperatures. In fact, something like 100 times the temperature of the core of the Sun.
He's right. Okay, that's very well said. That's a challenge a lot of people don't realize.
There is no material in the universe that wouldn't be instantly vaporized at the temperatures needed for fusion. So how are we supposed to even contain our fusion reaction, let alone crush it to the needed pressures?
Use something stronger than gravity.
Well, there are two broad approaches, inertial confinement and magnetic confinement. Inertial confinement attempts to slam nuclei together with some sort of shock. In 2022,
lasers.
The National Ignition Facility achieved net energy output for the first time by forcing fuel together with lasers. But it's not the first inertial confinement approach to succeed. The hydrogen bomb is a type of inertial confinement where the thing slamming nuclei together is a fission bomb and all.
Yeah, I guess you could argue it's inertial confinement. I mean, I've never heard it referred to in that particular term, but I mean, it's confinement. The main challenge of inertial confinement is it requires symmetrical uniform compression, which is why those lasers he showed earlier were in this little spherical thingy. The pressure's got to be directed inward. So the sun's actually closer to inertial confinement than magnetic confinement because, again, its gravity is pushing things down and it's doing it from all directions. Problem is, this is particularly inefficient. Now, the sun can get away with being inefficient just because it's so big. But the good thing about this is don't really have to worry about plasma control. At least not continuously. You got to get it set up, but it's easier to sustain once it gets going, provided that you get more energy than you put in. The sun just has so much reserves of fuel, which is why it can get away with it.
Cool atomic explosion. The latter is rather uncontrolled and so not suitable for sustained energy production. But even controlled inertial confinement approaches have the issue of rather bursty energy output, and so are generally not thought to be the most likely option for our first-generation commercial fusion reactors.
Yeah.
Those are more likely to be magnetic confinement reactors.
Inertial just wastes too much fusion fuel as well, whereas these magnetic ones are a bit more efficient.
The hydrogen in a reactor is so hot that positively charged nuclei are stripped of their negatively charged electrons, making a plasma of electrically charged particles that can be manipulated by magnetic fields. These fields are created by powerful electromagnets made from superconductors, and those superconductors have to be cooled to near absolute zero. So you make a little donut-looking thingy, or a tokamak, as people like to call it. And you got a couple of magnets. The circular one that you see here is the primary confinement. And then when you look at it from up and down, you have vertical loops. That's to stabilize and control your plasma. And since plasma is charged, the electrical current runs right through it. This center of a star hot plasma, mere meters away from matter that's colder than intergalactic space. So, to bottle our star, we have to create the largest temperature gradient in the known universe, which is, I guess, something to be proud of all on its own.
That is actually
Magnetic
really
confinement
cool.
reactors work by squeezing the plasma so it flows around a torus, and then compressing the torus with the magnetic field and heating it by blasting it with energy via particle beams or EM waves until fusion is achieved. This has to be done cleverly, because if you just run plasma in a circle, it leads to various instabilities that are fatal for your plasma and perhaps for your reactor.
And that's the biggest problem I see with at least fusion reactors coming out soon, because again, magnetic confinement appears to be winning and is undoubtedly the closest. Is the reaction's not very stable. There's not really, it requires extremely precise controls, which are being developed. Not saying it's impossible, but it just still remains a challenge.
Leading solutions for stable toroidal plasma confinement are the tokamak and the stellarator. The details of the differences aren't too important here, but tokamaks are more widely used, for example, by ITER, so I'll cover these just briefly. Tokamaks use three systems of magnets. The first system is the toroidal system, which is the main containment system and gives the plasma the donut shape. The next system is the poloidal system, which helps shape and position the plasma near the inner wall. This is to help compress the plasma for more reactions to occur.
Just like I mentioned
Lastly,
earlier.
the central solenoid drives the direction of the plasma, spinning the plasma in a circle. In contrast, stellarators combine all three magnetic systems into one using a 3D design, making them significantly more complicated.
The nice thing about stellarators, since they're all twisted together, is you don't need an internal plasma current, which means you're less likely to have stability issues. The main disadvantage of that is it's this weird looking coily springy thingy that is very hard to actually build, and also good luck trying to maintain it, just because it's a bizarre looking structure. And when you have a bizarre Frank Lloyd Wright type fusion reactor, given its operational parameters, the largest temperature gradient that we've discovered yet, well, maintenance can also be kind of challenging for something like that.
To some extent, the magnetic field is a relatively solved problem. There are no doubt refinements to be made in...
I don't like calling it a relatively solved problem. Even if it was, we're still a ways away from it. Even if it was a solved problem, It's more of about making incremental improvements, ways, efficiency gains. That's something that's still being worked on in any other power plant that uses steam in the secondary cycle. Yeah, the technology is a couple of hundred years old, but steam cycles with more modern control systems for your moisture separator reheaters and your feed water preheaters, yeah, that makes that steam cycle a lot more efficient. And by a lot, I'm still just talking a few percentage points, but a few percentage points, we're talking millions and millions of dollars. We're talking billions and billions of dollars over time if you look at the industry as a whole. I don't like the expression that it's solved.
Form of the field, and definitely in the generation of the field with new superconductor technology. That's something we can come back to another time. Currently,
especially since the superconductor stuff is also new, the control systems are also new. There's still plenty of opportunities for improvement.
The biggest engineering and research challenges in fusion is how to build the actual physical containment chamber for that field and the plasma it holds. How do we build a wall that can hold a mini sun? The magnetic field certainly helped by creating what's called a pedestal region where
I guess your other choice is to build wall of panels around the actual sun and make a Dyson sphere, but that requires us to move a fair bit higher up the Kardashev scale. So yeah, these are closer than that. I'll give fusion that.
Plasma is cooler and sparser relative to the middle where the fusion reactions are happening. This helps create a small buffer between the fusion plasma and the wall, so the material doesn't literally have to withstand contact with millions Kelvin plasmas, but it still has to do a lot. That wall is the first point of contact between the plasma and the outside wall, and we call the plasma-facing surface the first wall.
It's a reactor containment vessel, and just like in fission reactors, you're subjected to an intense neutron field, which causes degradation over time. From neutron embrittlement, it could cause swelling. But this stuff is more sensitive than what you see in a fission reactor. So, yeah, that's where your challenge is building is over there.
The field keeps the highest temperature parts of the plasma out of direct contact with the wall. A lot of energetic particles do reach it, and the wall needs to withstand that. It then needs to take the heat generated by this incoming radiation and transport it to somewhere useful to actually generate power.
Steam generator.
Finally, as if all this wasn't enough, the chamber wall needs to create new fuel for fusion. Let's look at these one by one. Within the coiled ribbon of the millions of Kelvin plasma, heavy hydrogen nuclei collide and release energy.
Yeah, you gotta find a way to keep your reaction going by adding more fuel.
Gamma rays and very fast-moving neutrons and helium nuclei. Those gamma rays and helium nuclei help keep the plasma hot. So hot it radiates X-rays. This thermal radiation bakes the outer wall of the chamber, and the wall has to very quickly conduct this heat to the cooling system.
That's the other thing. This thing is way hotter than that of a fission reactor, whereas fuel centerline temperature, which is very far away from the thing you're containing it in, can be on the order of thousands of degrees Celsius. But the reactor coolant system, basically your heat source for your steam generators, is only on the order of a few hundred degrees Celsius.
Or be at risk of melting. Even more energy is carried by the neutrons. These neutral particles are not affected by the magnetic field, and so they fly straight out of the plasma. They deposit kinetic energy into the wall, and this is the main source of heat energy from fusion. Some neutrons hit nuclei in the wall, potentially creating unstable isotopes. And
that's what's known as neutron activation. Something that isn't radioactive becomes radioactive when it absorbs a neutron.
Helium and hydrogen nuclei also end up with enough energy to escape the magnetic field and reach the first wall. Some of these are tritium nuclei, which are also highly unstable. As a result of the neutron and tritium bombardment, the wall becomes more radioactive over time.
It does. Note that tritium is also produced in fission reactors because we use water as a coolant. Hydrogen is used in water. Especially certain reactor designs, the CANDU reactors up in Canada, they use heavy water, which is deuterium 2O rather than your vanilla H2O. And that's more likely of making tritium because all it takes is one neutron to be absorbed and to make tritium. which is radioactive. If only we could take the tritiated water from a nuclear power plant and use that, and then make fusion fuel out of that with the tritium, but that would involve a lot of logistical challenges, to say the least.
Also erode the wall, with the wall's own nuclei getting smacked from the surface into the plasma chamber in an effect called sputtering. This degrades the shielding over time and also contaminates the plasma. Finally, an imperfect wall structure can lead to runaway instabilities in the plasma called edge localization modes. These can result in...
Everything's got to be nice and symmetrical, and if it can get distorted even a little bit...
Localized failures of the magnetic confinement, and to large amounts of energy being dumped into the wall, which is not good for the wall. This can also trigger larger magnetohydrodynamic instabilities in the plasma, causing the plasma to shed a lot of energy and potentially kill the fusion reaction. Assuming our wall can survive the above, the heat generated within the wall will be carried away by some working fluid. Water is a popular choice, but also molten salts and even lithium. The working...
You're going to want to start with water, because that steam cycle we know well. Yeah, combining molten salt, maybe if molten salt fission reactor technology was more mature, but one challenge there is you can stack some neutron embrittlement effects. The big challenge is just being able to extract the energy while also maintaining your plasma stability. I mean, basically getting it to pipe out through, put your water pipes or your liquid metal pipes or whatever to go in there. Yeah, because fusion it's so much more concentrated. It's also a much higher temperature. So I don't know if the first fusion reactors are going to be very efficient in terms of like actually making a power plant out of it. We haven't seen that at all yet. I mean, yeah, fusion reactors have been done, but no one's made steam or tried to turn a turbine with it or whatever.
Fluid both cools the wall and heats the fluid to the point...
At least not at scale.
It can turn a generator. Okay, so we've just generated electricity. Nice. But even if we got more power out than we used to create our plasma, this process is not sustainable.
You'd also have to make really big turbines or just use a lot of them. Not impossible, but just, again, it's a design consideration.
Tritium part of the fuel is enormously abundant. There are 33 grams per cubic meter of seawater, which means it's basically limitless. But the tritium is not abundant. It has a half-life of 12 years and so is almost non-existent naturally. The reactor has to make its own tritium. That's
basically use breeding, which is a thing that could also work in some type of fission reactors. But here, the breeding is critical to even get your fusion reactor to work, whereas breeding for a fission reactor is more of an added bonus feature for certain reactor designs. Still important, but here you're breeding on a much larger scale. Not to mention the whole no waste product with fusion. Well, you could argue, not counting all the stuff activated by your neutron field, it's more of the fusion reactants are potentially more hazardous than the fusion products. That being the tritium and how you take care of it. I know that's an effluent that is monitored very closely for fission reactors, so just something to be considered.
Not super complicated. Hit a lithium nucleus with a neutron and it'll split into two nuclei. So the trick is to place a
helium-4, also known as an alpha particle. Very stable.
Lithium behind the first wall. That wall will slow neutrons from the fusion reaction, extracting some of their energy, and the neutrons will then hit the lithium and breed tritium. Obviously, the lithium has to be replaced, but fortunately, lithium is moderately abundant with thousands of years' worth in the ground and millions of years' worth in the ocean. One major issue with this is that the fusion reaction doesn't produce enough neutrons to breed a sustainable amount of tritium. To deal with this, a neutron multiplier is needed. This is a layer of material that amplifies the neutron flux. One neutron goes in and two come out to feed the tritium breeder. That way, the fusion reaction replaces the tritium.
Not a real breeder if you don't replace it.
So, now that we know all the miracles that the reactor wall has to pull off, let's look at options for materials.
One example of converting but not breeding is you make plutonium-239 in a basic PWR, but it's not enough to replace all of your uranium-235. Even though plutonium-239 is actually more reactive, but You just don't make enough to fully replace it. You make a fair bit, though. About 30, depending on your core design, you can have something like 30% of your fuel be plutonium-239 by the end of your cycle. But again, just like with uranium-235, once you use it up, you use it up. You don't make plutonium-239 from more plutonium-239.
The most traditional pick for a fusion reactor first wall is the metal tungsten. It's metal, so it's structurally strong, and it has the highest melting temperature of all metals, so it can stay solid under heavy bombardment.
Yeah.
It's also less inclined to hold onto as many of the radioactive tritium as other materials. And very importantly, it has a low sputtering rate, fewer tungsten nuclei ejected into the plasma. However, it does have a major weakness with regard to sputtering, in that those tungsten atoms that do join the plasma have a pretty unfortunate effect. Tungsten has 74 protons in the nucleus compared to hydrogen's 1 proton. That means tungsten's electrons are much more strongly bound. So while the plasma's hydrogen is fully ionized, liberated of electrons, the tungsten atom will retain 20 or 30 electrons, even when inside the plasma. So now, when a tungsten atom bumps into another particle in the plasma, some of the energy of the collision goes into exciting one of those electrons. That electron then drops back to a de-excited state, emitting a photon in the process. And that photon then escapes the plasma, taking that energy with it. The larger the atomic number of the atom, the more electrons it can retain in the plasma.
Not the best for dose control either, because, talking about electrons, another word for free electrons is beta particles.
So the smaller the energy gap between electron levels, that means more opportunities to absorb energy from the plasma and radiate it away. This effect is called line emission cooling, and it's a great way to lose a lot of energy from your plasma very quickly. Yep. Even a little bit of a heavy element like tungsten in the plasma can make it very difficult to keep it hot enough to sustain fusion. Tungsten has major advantages, but the issue with pollution of the plasma was enough to convince the ITER team to try something different, at least to start with. In fact, they plan to go in the opposite direction to tungsten in terms of location on the periodic table by using beryllium for the plasma-facing wall. Beryllium is the fourth element on the periodic table, so even though it will end up polluting the plasma, those contaminants tend to be completely ionized. There are very, very few electrons left to radiate away the plasma's heat. In fact, beryllium actually removes pollutants. It can capture oxygen impurities, which themselves are released from oxidized metals in the vessel wall when the machine is running. Oxygen in the plasma can cause the plasma to cool just like tungsten. Beryllium has other major benefits. It has extremely high thermal conductivity, allowing it to quickly transfer heat from the front plasma-facing surface.
I like him kind of doing these little pros and cons lists, and thus far he actually seems quite unbiased in general. Way more unbiased than I am, I'll tell you that much.
To the back surface with the cooling systems. And one of the most compelling benefits of beryllium is that it acts as a neutron multiplier, doubling the neutrons available for tritium breeding. So
that's true, and that's a double-edged sword, like most things. As being a neutron multiplier, you're going to get a bunch more neutron embrittlement, but you ultimately need neutrons to breed, to make more of your fusion fuel to keep your reaction going. So it definitely has the scalability advantage.
What's the downside? Well, beryllium does have a much higher sputtering rate than tungsten, and even though the ejected impurities don't harm the plasma as much, this does mean the beryllium surface erodes much more quickly than tungsten, and that means the wall needs to be replaced more often.
You'll have even more neutron embrittlement, and can be a bit of an occupational hazard working with contaminated beryllium. I mean, I'm sure there's going to be a way to do it safely, but it's just an added expense. But yeah, I guess the neutron multiplier offsetting your sputtering rate if you're talking strictly about the production of plasma and keeping your reaction going. So it's pretty easy to see why they selected that.
Also, fluctuations in the plasma will induce electrical currents in the beryllium wall, and those currents experience massive forces in the strong magnetic field. This can damage the wall and even cause it to fail while the reactor is running. And a huge disadvantage of beryllium is that it's extremely toxic. Erosion of the wall fills the reaction chamber with beryllium dust, which cannot under any circumstances be allowed to get out of the reactor if you want to keep your nuclear engineers operational.
I appreciate the health and safety statement. Yeah, you're going to need more automated robotic maintenance systems than you do in, say, fission reactors. The main thing is you just want to make sure with fission is that you're fully cooled down, depressurized, and offloaded, which can be done by humans, albeit using remote tools like submarine cranes to offload the reactor fuel into the spent fuel pool, and then most maintenance that's done online, though, past the bioshield. And the reason why it's called the bioshield is you don't go past it while it's online, is you do use specialized drones or robotic systems.
Finally, beryllium is super rare. ITER would need 12 tons of the stuff for the first wall. ITER had originally planned a beryllium first wall, but
not really.
Just in 2023, they decided that the hassles outweighed the benefits and shifted their plan back to good old tungsten. This is a pretty safe choice for ITER as an experiment.
And that's one explanation for construction delay.
Facility, but for commercial fusion, some kind of neutron multiplier feeding the tritium breeder is needed, and ITER is currently testing various options. So, we still have the problem of tungsten polluting the plasma. There are other options for the plasma-facing surface, though. Boron is currently getting the most attention from the ITER crew since it's the next lightest element after beryllium. The idea is to build a tungsten wall and then sprinkle a little bit of boron powder into the reactor while it's running. This should then evaporate and coat the wall, reducing the amount of tungsten that cooks off into the plasma.
Interesting, because boron is used to shut down fission reactions.
Does have the icky side effect of retaining tritium, which means the inner wall could become dangerously radioactive over time. Meanwhile, going in the other direction on the periodic table from beryllium, we get lithium, which, if you remember, we were using to breed tritium behind the first wall. At first glance, lithium seems a non-starter for the plasma-facing wall because lithium metal has a melting point of 182 degrees Celsius. But who says the first wall really has to be solid? There's this idea.
See, this is one of the challenges with making something like ITER is if you're changing all this, it's a lot of scope change. I'm just trying to think the whole construction project management angle of this. And you're wondering why they have all these delays. And this isn't the only reason why it's facing delays either, because it's not just that. It's not just the wall. He's focusing on the wall in this video, but there's the superconductors, there's your crazy control systems, there's the building itself. I mean, it's massive. All the electrical connections.
To coat the reactor chamber in a layer of liquid lithium, which has many advantages. You can't really damage a liquid structurally. Seriously, go try hit a lake with a hammer and see what happens. Lithium nuclei,
I was not expecting that,
would end up in the plasma instead of the tungsten behind it. But this is actually good for the plasma. Getting plasmas up to fusion temperature requires physicists to add large amounts of energy, both with EM fields and with neutral beam injectors. Experiments like the lithium tokamak experiment beta at the Princeton Plasma Physics Lab suggest that a little bit of lithium in the plasma may help the plasma get to the temperature more easily. Finally, the lithium can even double as a coolant and the tritium breeder if it's moved through.
It could also make a really big lithium-ion battery. A lot of people are talking about lithium these days. It's kind of funny.
And behind the tungsten wall. As I said, ITER is supposed to produce its first plasma this year, but is projected to achieve its first fusion reaction in 2035, smashing two deuteriums together to produce helium-3.
Okay, yeah, he's clearly using the numbers from earlier. Yeah, unfortunately, both of those numbers have been punted to the right. With first plasma in 2030s and first fusion, you're lucky to have that by 2040, when my infant son will be more than old enough to drive. You kind of get into a weird time abyss with everything fusion, I'm afraid.
Now, its first commercial-grade deuterium-tritium fusion reaction is slated for 2039. If all that works, then I guess we build a lot of them. But it's also possible that one of the many smaller enterprises will beat...
And note that he just said commercial grade, because ITER doesn't have, like, steam generators or anything. I mean, the whole plan is it's just to be a science experiment. It's not designed to actually produce electricity. I'm assuming by commercial grade, even for them, we're talking 500 megawatts, which isn't that much compared to a fission reactor. The nuclear plant I worked at was over 3,800 megawatts thermal.
They certainly talk a big game, with some projecting first fusion in the next few years. But that's a story for another episode. Personally, I don't care who wins. I just want my infinite free energy so I can train a godlike LLM to take over writing space-time.
In the near term, you can use fission reactors for that. Thanks so much for the recommendation, and thanks so much for watching. I'll see you next time.